Hi, let's move on with the concept of potential and the calculation of potential energy using the concept of potential. Now you will recall from the previous video that potential is in a sense potential energy per unit charge placed at a point. Although that's not a very exact description, a more exact description would be that if we have a point where potential is V, and if at that point we place a charge Q, then the potential energy of the system will change by Q times V. And that's a more exact description that you might recall from the previous video. Now in this video we'll be learning some of those applications, but after calculating the potentials of a few simple charge distributions. And the first one that we have on our plate is a dipole. So we'll be calculating the potential due to a dipole first. So think of a dipole, carries a charge minus Q, has a charge plus Q. The distance between them is A, so the dipole moment would be Q times A. At a distance R from the midpoint of the dipole, we have this point here, and we are interested in calculating the potential here. Now to calculate the potential here, we'll be using the formula or the result for calculating potential of a point charge at a point close to it. Now the distance of the charge plus Q from this point would be R minus A by 2, and the distance of the charge minus Q from this point will be R plus A by 2. Right? So we have this distance is A by 2, and this distance is also A by 2. So the potential at point P will be given by 1 by 4 pi epsilon naught. Now the potential due to a charge Q at a distance R is 1 by 4 pi epsilon naught Q by R. So for the positive charge, the potential here will be Q by the distance from the point, and that distance here is R minus A by 2. And then potential due to the charge minus Q will be 1 by 4 pi epsilon naught times minus Q by R plus A by 2. I'm sure you will recall that in the expression for potential we substitute the charge with the appropriate sign that the charge should have. So this V is 1 by 4 pi epsilon naught. In the denominator we have R square minus A square by 4, and in the numerator we have Q R plus A by 2 minus R plus A by 2. So this potential V comes out to be, the R cancels, and A by 2 and A by 2 add up to A. So we have 1 by 4 pi epsilon naught Q A by R square minus A square by 4. And if of course A is small compared to R, we can make approximations. Initially let's just write like this: R square minus A square by 4. This QA is the dipole moment, and so we have V equals 1 by 4 pi epsilon naught P by R square minus A square by 4. Now if A is small compared to R, this is approximately equal to 1 by 4 pi epsilon naught P by r square, because a square by 4 can then be neglected. Now this potential will be positive over here because the positive charge is closer to the point and the negative charge is farther from the point, and therefore the positive potential is larger than the negative potential, and therefore we have a positive potential. But if along the axis you move to a point to the left of the dipole here, the negative potential will be higher and the positive potential will be lower. And in that case, the potential will be negative. Now, we'll be accommodating this fact in the formula, but a little bit later on. Now, this is calculation of potential of a dipole on the axial line. We now calculate on the equatorial line. Now on the equatorial line, potential calculation is actually that much easier. Minus q, we have plus q, and this is the equatorial line. Let's say we are looking at a point here at a distance r. Now the potential due to plus q and the potential due to minus q is the same, is equal in magnitude, but having the opposite signs. So the positive potential due to plus q and the negative potential due to minus q, they are both equal, and therefore the potential at this point will end up being 0. So on the equatorial line, potential is 0, and on the axial line, the potential is 1 by 4 pi epsilon naught p by r square. Now if you're looking at some arbitrary point, at some arbitrary point, now by arbitrary point I mean a point that's neither on the axial line nor on the equatorial line, then in that case we have this dipole having a dipole moment p. Then at a distance r we have a point, and we are interested in calculating the potential at this point. The angle here is theta. Now to calculate this potential, let's take the components of the dipole. The one along the r, this r is p cos theta, and the one perpendicular to r is p sin theta. Now this point is on the equatorial line of p sin theta, so p sin theta contributes nothing to the potential at this point. The only contribution to potential at this point comes from p cos theta, right? I'll repeat the argument. P sin theta contributes 0 to the potential at this point. Why? Because the potential due to a dipole on the equatorial line is 0. So P cos theta contributes to the potential here, and that contribution will be, that will be calculated according to this formula. We get V equal to 1 by 4 pi epsilon naught P cos theta by r square. In place of P now we have P cos theta, because that's the dipole we're looking at. Now what we can do is we can express this result in a slightly different way. 1 by 4 pi epsilon naught P dot r by r cube. Now the numerator is P r cos theta, and r therefore cancels, and you end up with the same thing. But then this expresses more than this result does. Why? Because this also incorporates the sign. You recall I mentioned here that this can be positive or negative. Now this formula actually incorporates that positive or negative. If for instance this is the dipole and we are looking for the potential here, this would be R, and now P and R are in the same direction and the angle between them is 0, cos theta being 1, the potential here comes out to be positive. But if you took your R in the opposite direction, this way, if the R was this way, then the angle between P and R would be 180 degrees, and for a 180 degree angle the cos theta would be -1, and with cos theta equal to -1, potential would be negative, and therefore this formula incorporates the sign as well, and therefore it's a more complete formula for calculating potential due to a dipole. We will now be calculating the potential of a uniform circular ring carrying a uniformly distributed charge. So this is the ring. It carries a charge Q and has a radius R. It's kept in the YZ plane, and the x-axis is the axis of this ring. The charge Q is distributed on it uniformly, and we are interested in calculating the potential at a point here which is distant x from the center of the ring on the axis of the ring. The x-axis is the axis of this ring. Now to calculate potential at this point, it's a continuous distribution of charge. What we need to do is we need to break up this charge into tiny elements and calculate potentials of those small elements, and eventually do a summation of those potentials, and that's exactly what we'll be doing. Consider a small charge element here carrying a charge dq. Now this dq is at a distance root r square plus x square from this element, is distant so much from the given point where we are interested in calculating the potential. Now the potential due to dq at this point, let's call it dv, will be equal to 1 by 4 pi epsilon naught dq by root of r square plus x square. I've used the formula for potential due to a point charge. So for a point charge, you remember it's 1 by 4 pi epsilon naught times q divided by small r, where small r is the distance from the point charge. In this case, this distance is small r here. So this is dv. Now that's the potential due to a charge element carrying a charge dq. Now the potential v due to the entire ring. Now since potential is a scalar, we just need to do a simple summation, and therefore all this constant stuff comes out. For all the points on the ring, x doesn't change, r doesn't change, so r and x are also constants, therefore they come out of the integral, and then we do a summation of dq. And once we do a summation of dq, that is, we add all the dq's, and if you add all the values of dq, you get the total charge q of the ring. And so the potential at the center of the ring will be equal to 1 by 4 pi epsilon naught. This on summation becomes q divided by root of r square plus x square. That's the potential due to a ring. So we've calculated here the potential due to a ring. And next on the line is potential due to a uniform disk. Now the difference between a ring and a disk is that the disk has charge distributed all over it on the entire area, whereas the ring has a charge only on the circumference. The disk has a charge on the entire area. So just to indicate that fact, I'll do a little bit of shading here. The disk carries charge all over its area. Now this is the center of this disk. The radius is r. Sigma is surface charge density. That's the charge per unit area. Now we are interested in calculating the potential at a distance x from the center of the disk on the axis of the disk. Now to do this, what we will be doing is, we already know how to calculate the potential of a ring. What we will do is, we will break up this disk into small ring elements. We'll calculate the potentials of those ring elements, then do a summation and get the potential. It's a scalar, of course, and therefore the summation is that much easier. It's just a simple summation, no components need to be taken. So let's consider a ring element here. Now this ring element has a radius small r and has a width dr. This is the ring shaped element that we are considering. Now the charge on the ring element can be calculated by multiplying the area of the ring with the surface charge density. So if you take this ring out of the disk, spread it straight, it has a length equal to 2 pi r and a width dr. So if you take it out and spread it over here like this, it has a width dr and a length 2 pi r. Correct? So the area of this ring is dA, and that's 2 pi r, the length, times the width dr, and therefore the charge on it, that's dq, will be given by 2 pi sigma r dr. That's the charge on it. Now because of this ring, the potential at this point dV can be calculated using this formula for the ring. In place of q, we'll of course be using dq. So we have 1 by 4 pi epsilon naught 2 pi sigma r dr divided by, we had r square plus x square here. Remember, this capital R here was the radius of the ring. The radius of the ring here is small r, and so we have small r square plus x square. That's dV, the potential due to the ring element. So we have some cancellations, 2 pi cancels out, and so dV now equals sigma by 2 epsilon naught r square plus x square to the power minus half. See, this was 1 upon root r square plus x square. So what I've done is I've taken it in the numerator, the power becomes negative, r square plus x square to the power minus half times r dr. And we will be integrating all over the disk. The disk is actually made up of all these rings, and we will be doing a summation of the potentials of the rings. So the innermost ring, the smallest ring, has a radius 0, and the outermost ring has a radius capital R. So we do a integration from 0 all the way up to capital R, the variable of integration being small r. Now if you recall the simple integral that you have it in front of you, r square plus x square to the power minus half into r dr. Now r square plus x square, just look at r square plus x square. X square is a constant, its derivative would be 0. The derivative of r square would be 2r. Now here we do not have 2r, but we have r. So what we do have is a function raised to the power n into, well, this could have been the derivative had there been a 2, and we'll do that. We'll put a 2 in there. So we have a function raised to the power n into derivative of the function into dr. Now to make this the derivative of this function, we multiply here by 2 and divide by 2 as well. So we now have a function here raised to the power n into the derivative of the function times dr. Now when we have this kind of a situation, let me remind you of this integral form. If we have fx raised to the power n into f prime x, the derivative into dx, the integral comes out as fx to the power n plus 1 by n plus 1 plus c. I have explained this form in my video on integration, and in case you wish to see this in action in a couple of simple examples, you can go back to my video on integration and review this. Now we come back here to this integral. Of course, when we integrate, this dv now becomes v. We are calculating this v now. Sigma by 4 epsilon naught, and here we have r square plus x square to the power, now n plus 1. You have this n here was minus half, n plus 1 will be plus half. You know, we had n equal to minus half here, n plus 1 will therefore be plus half, divided by that power plus half, and the limits are from 0 to r. So v equals sigma by 2 epsilon naught now, and we have inside the bracket here root of r square plus x square minus, when you substitute 0 in place of small r, you have root of x square here, which obviously is x. Another interesting observation that you can do is, you remember that the electric fields are also along the axis in both the cases. So electric field would be simply equal to del V by del x minus del V by del x, and you can check this out. Calculate del V by del x in both the cases and take a negative of that del V by del x, and I'm sure you'll easily be able to figure out that minus del V by del x in both the cases is equal to the electric field. That's the gradient of potential concept that we learned in the previous video. So we've calculated the potential due to a ring, we've calculated the potential due to a disk. We now move on and discuss the potential due to spherical objects. So we'll first be taking up a spherical shell, and then we'll talk about solid spheres as well. So we're starting with spherical shell. Now what's a spherical shell? It's a spherical body where everything is there on the surface. The inside or the interior carries nothing. In this case, we are really talking about charge being entirely on the surface. So we have a spherical object in which the charge resides entirely on the surface. The interior carries no charge. So we have a spherical surface carrying a charge Q, distributed uniformly all over it, and we are interested in calculating its potential at distances small r from the center. Now what we'll be doing is we'll be calculating the potential here where small r is less than capital R. If small r is less than capital R, then we are inside the sphere, and if small r is greater than capital R, then we are outside the sphere. Now to calculate these potentials, we'll use a clever little trick. You will recall that a spherical shell behaves like a point charge placed at the center when you're looking at points outside it. So if you're looking at this point here, the shell is behaving like a point charge placed at the center. So we are first examining points in the exterior of this shell, and exterior means small r, the distance small r from the center is greater than capital R. Now over here, as I said, this charge behaves like a point charge placed at the center, and therefore we can calculate the potential just like that of a point charge placed at the center. So if this entire Q is a point charge and it is placed at the center, then potential will be 1 by 4 pi epsilon naught times Q by small r. That's the potential just outside this shell. Now if we go inside interior of the shell, that's when small r is less than capital R. Let's take this up over here. When small r is less than capital R, you're inside the spherical shell. We are interested in calculating the potential. Now what we can do is we can break this up into a couple of steps. We can first take up the potential just outside the surface, and the potential just outside the surface, using the same result, will be 1 by 4 pi epsilon naught Q by capital R. Correct. So that's the potential just outside the surface. Now as you move inside the surface, then what happens? That's when small r is less than capital R. This is what we are interested in. Now if we bring a unit positive charge from infinity all the way up to the surface, then the work done will be negative of this potential, right? Since potential is negative of that work done will be negative of this potential. So if I bring a unit positive charge from infinity up to this point, then the work done by the electric field on that unit positive charge will be negative of this potential. That's how potential at a point is defined. So work done on the unit positive charge as it is brought from infinity to this point by the electric field is negative of this quantity. And then as we move further from here to here, from this point, let's say A to this point B, from A to B, there is no work done by the electric field because the electric field inside the shell will be zero. Since the field inside the shell is zero, no work is performed by the electric field on the unit positive charge being brought from infinity to this point. So as we bring a unit positive charge from infinity to A, work done on it is minus Q by 4 pi epsilon naught R, and then from A to B no work is done. So from infinity to B, the total work done is negative of this value, and therefore the potential at B will be negative of that work, which is now 1 by 4 pi epsilon naught Q by R. Now let me remind you of everything. I bring a unit positive charge from infinity to B. The total work done on it by the electric field is minus Q by 4 pi epsilon naught R, and therefore potential is negative of that work, which is now Q by 4 pi epsilon naught R. What you notice is that the potential inside the shell is not even dependent on small r. It depends entirely on capital R, the radius of the shell. So it's a constant quantity, and if you were to draw a graph of this potential, that is a graph depicting variation of potential V versus the distance small r from the center, you will get something like this: 1 by 4 pi epsilon naught Q by R on the inside, and then as you move outside, this is where small r becomes equal to capital R. When small r becomes greater than capital R, you end up having a rectangular hyperbola for this function here. So that's the potential due to a spherical shell. Now, now that we understand how a spherical shell produces a potential, what kind of potentials it produces, we move on now to a solid sphere. Now for a solid sphere, the difference from spherical shell being in the fact that a solid sphere carries charge throughout its volume, whereas a shell carries charge only on its surface. So for a solid sphere, the charge is distributed in the entire volume of the sphere. So we have a solid sphere of charge here, has a radius r, it carries a charge q, and the charge q is uniformly distributed in its entire volume. So charge here is of course q, and initially when we calculate potential at a distance small r from its center, with small r being greater than the radius of the sphere, over here in the exterior of the sphere, that's outside the sphere, small r will be greater than capital R. Now for points outside it, a solid sphere also behaves like a point charge placed at the center. This, we have had a discussion on this when we applied Gauss's theorem to spheres. So potential outside the sphere will be calculated just like the potential of a point charge. So if you consider the entire Q charge to be concentrated at the center, then the potential here is 1 by 4 pi epsilon naught Q by small r. Now what about the inside of the sphere, or let's say first at the surface of the sphere? On the surface where small r equals capital R, your potential is going to be 1 by 4 pi epsilon naught Q by capital R. So the potential now is 1 by 4 pi epsilon naught Q by capital R on the surface. Now to calculate the potential inside the sphere, let's say we have this point here at distance small r from the center, and we bring a unit positive charge from infinity to this point, calculate the total work done on it by the electric field, and then we take a negative of that work done and we get the potential at this point. Now since we know the potential at the surface, work done on a unit positive charge as it is brought from infinity to the surface, that work will be negative of the potential at the surface. So work done from infinity all the way up to the surface, that work is Q by 4 pi epsilon naught R. Then we need to further calculate work done by electric field in moving that unit positive charge from this point to this point. Now when we are at a distance x from the center, the electric field will be 1 by 4 pi epsilon naught Qx by r cube. This is the formula for electric field in the interior of a solid sphere. In case you do not recall this, go back to that video where we've discussed fields due to spheres when we applied Gauss's theorem in calculating electric field. So in case you're not able to recall this, go back to that video and see how we arrived at this result. This is the electric field. Now at this point, if we bring the charge inward, so this is let me draw this here. This is x and the electric field E is this way, and we consider a small displacement ds. Then the work dW done by the electric field on a unit positive charge, it will be equal to 1 by 4 pi epsilon naught Q by r cube x into dx negative. We are assuming the charge to be positive, so the field is outward and the displacement is inward, the opposite direction, and therefore the work done is negative. We had to have a ds here, sorry. Now this ds is actually a negative change in x. ds is towards the center, right? So ds is a negative change in x. It's a decrease in x, so negative change in x. So we replace ds by minus dx, and dw therefore comes out to be 1 by 4 pi epsilon naught q x dx by r cube. Now we were interested in calculating the work done from the surface up to this point. So x varies from capital R to small r, and therefore total work done from surface to this point will be equal to q by 4 pi epsilon naught r cube integral of x dx from capital R to small r. Now this work done comes out to be q by 4 pi epsilon naught r cube x square by 2 from r to r, and therefore the work will be q by 4 pi epsilon naught r cube this 2 merges with this 4 becomes an 8, and here we have small r square minus capital R square. That's the work done. So the total work done in moving a unit positive charge from infinity to the considered point P over here, this is, let's say this is point P, the total work done from infinity to P will be equal to the sum of these two. So this plus this, so we have minus q by 4 pi epsilon naught r minus q by 8 pi epsilon naught r cube. I'll put a minus sign here and then I'll be interchanging these terms, r square minus small r square. Now you add them up, you get this total work from infinity to P equal to 1 by 4 pi epsilon naught q by 2r cube into 3r square minus small r square. So negative of this, of course, this is the work done, and therefore the potential at point P inside the sphere becomes negative of this work, and therefore equal to 1 by 4 pi epsilon naught q by 2r cube into 3r square minus small r square. That's the formula for potential inside the solid sphere. Outside it, this was the formula, and that's the formula for the surface. Now if you were to calculate a graph for this, V versus small r, here small r becomes equal to capital R. In the interior of the solid sphere, it's dependent on minus r square. So in the interior it's a parabola, and as you get outside the sphere it's a rectangular hyperbola because it's inversely proportional to r. So you get a graph that looks like this. This is how potential due to a uniform solid sphere varies with distance from the center. So we've completed the calculation of potential due to spherical charge distributions, and I guess this is where this video will probably have to end because it's getting a little long. We will be calculating potential energies using the concept of potential in our next video. Thank you very much for watching.